Welcome to this lecture. This is the first lecture of week 3. In the previous week's lectures, we have started discussing about sequences of random variables and their convergences. In particular, we have recalled the description of almost everywhere convergence or almost sure convergence as we have seen it, and we have seen a couple of examples involving measurable functions and their almost everywhere convergences. In this lecture, we will continue that same discussions, but focus mostly on the random variable situation, meaning we will be talking about almost sure convergences. So, without further delay, let us move on to the lecture notes. So, as I pointed out, we are going to talk about the almost sure convergences of random variables. So, here the first thing that we are going to focus on are certain equivalent formulations of this type of convergences, meaning we are going to look at different criterias which are equivalent to the definition we have stated. Now, for notational convenience, we will continue to use one single notational scheme that we are already given one probability space which we denote by omega fp, and a general sequence of random variables shall be discussed in terms of these xn's. So, now with xn's we will put certain appropriate conditions and discuss the measurability and other relevant convergence conditions. So, let us start with this first equivalent statement for almost sure convergence. So, we start with this basic statement that xn converges to x almost surely if and only if for all epsilon positive this limit is 1. So, let us try to focus mostly on the description of the probability of the events that we are looking at here. So, what we are saying is that first you look at a natural number m and then look at all natural numbers following after that starting with m, right. Now, our interest is in this event actually, that for all n exceeding the given number m, I want to see whether the random variable xn minus x is close to the number epsilon or not, or below epsilon or not. So, here we are essentially checking whether the xn's are close to x or not. Now, these events that we have described here, we are going to look at the probability of that, and the equivalent condition that we are stating as part of the proposition says that these probabilities must go to 1 as m goes to infinity. Now, another way to state this same condition in terms of set theoretic notations is like this. We see that we have imposed a condition involving n and n should be greater or equals to m, right. So, therefore, what we are actually asking that this condition should continue to hold for all such n exceeding m. So, therefore, for n equals to m to infinity, I want these events to occur, and therefore, I am looking at the intersection of all these events, and the condition essentially getting restated in this form that for all epsilon positive this limit of probability should be 1. So, let us try to see why this condition is equivalent to the condition of almost sure convergence. So, we start with the proof of necessity, meaning we will assume first that the sequence converges almost surely and then show that this new condition we have just stated in terms of the appropriate limits of probabilities, that should be 1. So, let us see. So, we follow the definition and let us say I start with a p null set n. Here what we would like to have is that on the complement of that null set I should have the pointwise convergence. So, this is just the definition I am restating. But now let us bring in those probabilities that we are interested in. So, you fix this number epsilon. So, this is arbitrary but fixed, and define a sequence of events which we are going to deal with. So, these are now indexed by this number m, and what we want is that these are the exact events that was described in terms of the condition that we want. So, therefore, let us focus on these events and give them a name. So, we are going to call them as am for notational convenience. Now, we are going to look at all these events starting with m equals to 1, 2 and so on, but essentially we will be interested in the probability of these events as m goes to infinity. So, let us see, as already pointed out, since we are asking for this condition to be held for all n exceeding m, therefore, we are essentially asking for this intersection of these events. Now, using the pointwise convergence that we already am given in terms of the almost sure convergence, what we claim is that on the complement of that null set, I have the pointwise convergence of this sequence of values. Note here, what we are asking is that these are certain real numbers xn of omega. So, this is a sequence of real numbers which converges to this number x of omega. Now, here use this pointwise convergence and use the above epsilon and follow the definition of a limit as we know about it for convergence of real valued sequences. So, let us see, what we shall have is a positive integer m exceeding which we shall have certain error bounds which will be smaller than epsilon. But now remember, we are doing it based on the epsilon and for each fixed omega at a time. So, therefore, this number will depend on both the sample point small omega that we are using and also the epsilon parameter that we are using to treat the error. So, therefore, what we will have is that exceeding this number capital M, we will be essentially having this condition satisfied, so that the limit of xn of omega essentially converges to x of omega. We are just rewriting the definition of pointwise convergence here. But consequently, we note that as soon as this condition is satisfied, we immediately have that for all such n which exceeds this number capital M, we will have the point small omega is in an, meaning that all those conditions are getting satisfied for all n after this point onwards. So, therefore, omega is in an whenever n is greater or equals to this number capital M. Hence, what we have actually done is that we have actually started by fixing that epsilon positive, but for that what we have managed to show is that for all small omega in the complement of that null set that we are working with, those small omegas are again in the sets an, and therefore, what we claim is that no matter what small omega you choose, there is always a number capital M exceeding which the omegas are in an, and therefore, all the points of n complement must be in one of the ans from some stage onwards, right. So, therefore, what is going to happen is that n complement essentially turns out to be contained in the union of these sets, but n is a set of probability 0 and therefore, the complement of that has probability 1 and this is a superset of n complement and hence the probability of this union must be 1, alright. And hence what we essentially end up having is the condition that we wanted, because this probability is exactly what we are stating in the condition. So, let us just go back to the condition once more. So, we stated in terms of the limit of these events that you will see that limit of intersection of all these things must be 1, but what we have essentially end up having is that the limit over all this union essentially is 1. So, that essentially proves the statement, alright. But now, let us try to prove the converse part, that what we want here is that we want to first fix epsilon positive and starting with the condition that is given to us, we want to show that the almost sure convergence holds, meaning I want to figure out a null set on the complement of which the pointwise convergence should hold. Now, what we have are these sets AM, we continue using the same notations for notational convenience, and as per the given statement I end up having this condition that the probability of this union of these sets must be 1. But now, what we want to do is to focus on that value epsilon that we are given. We see that as per the condition, all such limits are 1 for all such epsilon positive, right. So, what we are going to do is to focus on the dependence of these sets on this parameter epsilon that we have kept fixed. So, what we do is that we want to explicitly write out this parameter epsilon as part of the notation. So far whatever notation we have been using, we have been writing it as A subscript m. Now, we will write explicitly A subscript m comma epsilon to also highlight the dependence on the parameter epsilon. So, let us rewrite this condition again. So, what we are essentially saying is that for all epsilon positive, what we have is that probability of this union of these events must be 1. In particular, what we do is that we choose our epsilons to have very specific values of the type 1 over L, where L is a natural number and L we will take to be increasing to plus infinity. But then what is going to happen is that for every fixed L, epsilon equals to 1 over L gives us the probability of this union to be 1, right, and therefore, what we first observe is that this union of these events in terms of the parameter L actually has a nice increasing or decreasing feature, that as long as L increases, the union of these sets will decrease, okay. And therefore, what we do is that we use the continuity property of the underlying probability measure that we are using. Here, if we take the intersection over all these sets now, so you see the innermost union is in terms of L, and as L increases, we have pointed out that this union decreases. So, if we take the complete intersection over the parameter L, then we will use the continuity property of the probability measure to claim that this limit of individual probabilities, but based on only L here, that should be the same, okay. So, we have essentially used the continuity property of the probability measure here, alright. But then you note that for every fixed value of L, this inner quantity is 1, and therefore, this limit must be 1, and hence what we have managed to show is that on this set the probability is still 1. So, what we have essentially used is that if you have a sequence of sets which has full measure, which was indexed by this number L, now as L increases, the sets were decreasing. So, therefore, the complete intersection should also have full measure, which is the probability 1 case as appears here. So, that is what we are using here. So, now on this set of full measure, we take a point small omega. What we end up having is that on this set of points, what we have is that this sequence of values xn of omega, that sequence must converge to x of omega. Why? Because what we are saying is that as long as omega belongs to this set, that means that xn of omega minus x of omega, that value, if you look at the modulus of that, that must be controlled in terms of 1 over L, and hence as L increases 1 over L decreases. So, therefore, xn of omega minus x of omega must be very very small, and we can make it as small as we like by taking larger and larger values of L. Here what we are essentially varying is the number small n, so that xn of omega gets closer and closer to x of omega, and hence what we ended up having is the convergence for this set of points. So, whenever omega comes from this set of full measure or full probability, then we have the pointwise convergence. So, this in principle essentially what we have to just do is the look at the complement of this set of full measure that has measure 0, and therefore, we are essentially saying that we ended up having the almost sure convergence of this sequence of random variables xn to the random variable x. So, we ended up having the almost sure convergence. So, we showed both sides of the statements that if we start with almost sure convergence, then that condition can be restated in terms of this limit of probabilities being 1. On the other side, if you start with this limit of probabilities being 1, you end up having that we actually managed to show the almost sure convergence. So, therefore, we have the equivalence as stated as part of the proposition. So, let us move on. What we now are going to do is to restate this new condition that we obtained into various other equivalent formulations. Okay. So, the first one is this. So, earlier what we have been looking at was xn minus x should be less or equals to epsilon for all n exceeding m. So, that was the description of our event, and what we said is that limit of these probabilities should be 1. Now, if you take complement of these events, that limit must go to 0, So, that is just following the property that probability of any set can be written as 1 minus probability of the complement of the set. So, that is all we are going to use now, but then the innermost condition that we have, we just have to take the complement of the description. So, therefore, first of all this bound becomes greater than, because that is the opposite kind of event, but then earlier we wanted to have the condition for all n exceeding m. So, now in the complementary situation we just want it to happen once. So, therefore, it happens for some n exceeding that value m. So, that describes the complementary event, and what we essentially have, just by complementing it we ended up having the probability of these events must go to 0. So, this is now an equivalent condition to the equivalent condition that we found in the previous proposition. But then again you see, we want this new condition that we have just stated for some n exceeding m, but then again this can be restated in terms of the set theoretic notation in terms of this union of these events, since we want our point small omega to fall in at least one of these cases. So, therefore, we end up having the set theoretic union here, and again we just state the same condition that limit of these probabilities must be 0. Now, we recall another interesting structure that we see in terms of the sequence of events. So, let us say a n is any sequence of events. So, let us forget about any notations a n that we have used earlier. Now, we are taking any arbitrary sequence of events now. So, for that we recall the definition of lim sup of this sequence of sets. So, this is also written in terms of this event that a n happens infinitely often. But then what is the mathematical description? It is this, that first you look at this innermost union and then you take this outermost intersection. So, this complete construction will give us the lim sup of this sequence of events a n. Now, you see that earlier what we have written in terms of this probability of these unions going to 0, that can actually be restated in terms of this lim sup condition or infinitely often condition by saying this, that for all epsilon positive we must have xn minus x, that value in modulus exceeding epsilon infinitely often, that should not occur, okay, and that is what we are essentially saying, that it must happen with probability 0. So, this is exactly the limit of those probabilities that we have looked at. So, this is in terms of probability of the lim sup of the events. Alright. So, hence what we have done so far is that we started with the basic definition of almost sure convergence, and we have restated it in 2 or 3 different languages, and all of this used basic set theoretic operations. But now let us look at it from another perspective. So, we start with again the basic definition of almost sure convergence of random variables. So, here what we have is a p null set which we denote by n, such that on the complement of the null set we have the pointwise convergence. Now, recall that the real line is complete, meaning that if you take any Cauchy sequence in the real line, it must converge, and conversely we also know that any convergent sequences are Cauchy. So, what we are going to do is to look at this real valued sequence xn of omega and converging to x of omega, and we are going to restate in terms of the Cauchy condition. So, this is another restatement of the earlier statements that we have so far discussed. So, let us see what is the condition in terms of the Cauchy property. So, what we are now going to look at are the fact that this xn of omega, for omega coming from n complement, these corresponding sequences must be a Cauchy sequence in the real line. Therefore, what we are stating now is that for all epsilon positive, there is now a positive integer depending on that omega and epsilon of course, such that for any two natural numbers n and n prime exceeding that level capital M, what we will have is that the terms should be close together, alright, that xn of omega and xn prime of omega should not differ too much, and that can be controlled by this parameter epsilon. So, you fix the epsilon, we can find that number capital M such that this happens. So, this is exactly the Cauchy condition. So, this is essentially a restatement of the convergence statement that we made earlier in terms of the limit of probabilities. Now, again this Cauchy condition we can also restate it in another formulation, that it is also equivalent to the fact that for all epsilon positive, what we will have is that probability of that the subsequent terms for n primeth terms exceeding that number epsilon for some n and n prime exceeding certain level m, that happens with probability 0 in the limit. Okay. So, this is just another restatement of the Cauchy condition. So, you can just try to figure out how you get this. Okay. So, please check this out. Alright. So far what we have done, again let us just formalize. We started with the basic definition of almost sure convergence. We restated in terms of limit of probabilities of certain events and also in terms of the lim sup of certain events. But then we finally restated everything in terms of the Cauchy condition in terms of the convergence of xn of omega. Alright. Now, let us try to use these results that we have seen so far. So, here what we want to point out is that we have so far focused on all the convergences in terms of random variables in terms of the almost sure convergence. But just as a quick comment, let us look at the corresponding convergences in terms of the measurable function setting. So, in terms of measurable functions, we have already seen examples of almost everywhere convergence, but then again we are interested in these equivalent conditions. It so happens that if you start with a finite measure space, meaning you have a measure mu which is finite, then you can actually redo all these arguments that we performed for random variables and a probability measure. We can redo all these arguments and end up with a similar condition. So, let us state this. So, the almost sure convergence for this sequence of measurable functions fn to a measurable function f can be equivalently stated as this, that for all epsilon positive, this union of these events or these sets have measure 0 in the limit. So, this is just essentially a generalization or repetition of the argument that we have been discussing for random variables. Alright. So, now we have a better idea about almost sure convergences in terms of multiple other equivalent conditions. So, now what we are going to do is to recall the connection with another type of convergences that we have already seen. So, this is the comparison between this almost sure convergence and convergence in the LP situation. Recall earlier that we have discussed about these LP spaces, and here we are interested in the range of P being between 1 and infinity, 1 included and infinity excluded. So, we recall certain result that we have already discussed earlier. So, we start by recalling proposition 8 from week 1. So, what we have seen there was a version of the dominated convergence theorem stated as follows, that we have a almost sure convergence sequence of random variables going to x, and if you have a random variable y in LP such that modulus of xn is dominated by y for all n, then you must have that all these random variables are in LP, and moreover this convergence actually happens in LP. So, together with certain appropriate integrability bound, if you have the almost sure convergence, then it implies the LP convergence. So, that was the DCT application that we have already seen in the discussions of week 1. We also recall another result that we have seen in week 1. So, this was in terms of LP convergences as part of the hypothesis. So, this was in theorem 11 again from week 1. So, we start with this sequence of random variables converging to x in the NP spaces. Then what we observed was that there exists a subsequence, in fact we explicitly constructed such a subsequence of the sequence of random variables such that this subsequence converges to the limit random variable in the almost sure sense. So, just to clarify, both of these results were stated more generally in terms of measurable functions and with any underlying measure, but here we are restricting our discussion to the case of random variables with the underlying probability measure. So, this is just a specific case of the general case of measurable functions in terms of the underlying measures. But now let us look at the situation now, that we have seen under certain conditions that there is certain link between the LP convergence and the almost sure convergence. But let us try to properly clarify if one of them implies the other or not. So, we discuss this, but in terms of examples, and these examples will make the relationship clear. So, start with this set omega being the closed bounded interval 0 1 in the real line. Now, here we can look at the Borel sigma field. This you can construct by looking at all the open sets inside the set omega through the subspace topology. So, that is one way to construct this Borel sigma field. Another way to get this is that you just restrict all the sets coming from the Borel sigma field on R and look at the collection of sets intersected with the 0 1. If you look at this collection of sets, that is exactly this Borel sigma field on 0 1. Alright. Now, what we do is that we also look at the Lebesgue measure lambda on the real line, but restrict it to this specific collection of sets. But now what will happen is that lambda of the whole set omega is exactly equal to lambda of 0 1, which gives you the length of the interval, which is 1. So, therefore, this here turns out to be a probability measure. The restriction of lambda to the set omega is a probability measure. So, now what we have ended up obtaining is that on omega together with the Borel sigma field and the restriction of lambda, we have a probability space. What we do is that we discuss explicit sequences of random variables on this probability space. So, let us look at this situation, that for omega coming from 0 to 1 over n, where n is some natural number, if you take such an omega coming from this interval, we assign the value as r to the power n, where r is some fixed real number given beforehand with r being greater than 1. So, let us take such a choice of number r and look at this sequence of random variables defined through this way, that on this say intervals we assign the value r to the power n, otherwise 0. So, that is how we construct new sequences of random variables. Now, we are interested in the convergence of this explicit sequence of random variables. Now, what happens here is that let us look at the p norm of these random variables. This is nothing but the pth root of the pth absolute moments of the random variables xn, and if you compute this, this will turn out to be pth root of this expression. Now, by our choice we have taken the number r being greater than 1, and what you can show is that as n goes to infinity, these quantities actually goes to infinity. So, this there is a correction here that will be made to the lecture notes, which will be finally handed over to you. So, these quantities actually go to infinity, and hence these random variables actually do not converge in LP. So, this is something striking here, that we have noted that the p norm of these random variables essentially explodes to infinity. So, as a limit it is infinity, and hence the sequence cannot converge. But now let us look at the situation in terms of the almost sure convergence. Now, on the set open 0 to closed 1, so essentially we are excluding the point 0 from our discussion, but for all other values of omega, if we choose a large enough n, what we have is that omega does not fall in the interval 0 to 1 over n. So, if you choose omega to be positive, if you choose any omega to be positive, so there exists a number n such that omega is greater than 1 over n. So, therefore, omega is not in the interval 0 to 1 over n. So, therefore, for all such large values of n, the values of xn of omega must be 0. So, after a certain stage onwards, depending on the value small omega, you have the limit being 0, alright. So, therefore, on the set of points which is excluding 0, for all other points we have managed to show that pointwise limit of xn of omega is actually 0, alright. So, therefore, if we choose our null set to be this singleton 0, remember the Lebesgue measure assigns 0 mass to singleton sets. So, therefore, this n which is a singleton set 0 is a lambda null set. on the complement of this we have essentially shown this pointwise convergence to the value 0. So, therefore, what we claim is that this sequence of random variables converges almost surely to the degenerate random variable at 0. So, this example shows that even if we do not have the LP convergence, we may have almost sure convergence, alright. So, another way to state this is that given a almost sure convergence sequence here, we do not have the LP convergence. So, almost sure convergence does not imply LP convergence. To claim LP convergence through almost sure convergences, we need additional integrability conditions which is given by the DCT as we recalled earlier. But let us now look at the opposite situation. We will show an example again where we will have LP convergences but not almost sure convergences, and it will end up showing that LP convergences do not imply almost sure convergence. Again, just to compare with the result we have seen earlier, what we have said is that given a LP convergent sequence, we can extract a further subsequence which converges almost surely. It says nothing about the original sequence converging in the almost sure sense, and what we are going to show here is that in general we might not have that, meaning we might have LP convergent sequences but which do not converge in the almost sure sense. Let us see. So, we continue with the probability space that we have constructed earlier on the set 0 1. We continue with that probability space, but we construct a triangular array of random variables indexed like this. So, we start with x11, then we take x21, x22, then x31, x32, x33 and so on. So, more generally we will have indices n and m, where m is between 1 and n varies from 1, 2, 3 and so on. So, n essentially looks at the row number. So, n equals to 1 gives x11, n equals to 2 gives the second row and so on, alright. So, now we define this new sequence of random variables here. So, what we do is that given these values m and n, we look at this interval open m minus 1 by n to m by n, okay. So, that is a sub interval of 0 1. So, on this interval we look at the indicator function. So, meaning if my omega belongs to this interval, I will assign the value 1, otherwise I will assign the value 0. Now, what we do is that we have this triangular array of these random variables. Now, what we do is that we read them row wise from left to right, meaning we start with the first row, we have only one single random variable here, we read it, then we move on to the next row, but start from the left and move on to the right side. So, we will have x21, x22, then move to the third row x31, x32, x33 and so on. So, likewise if we follow this procedure, we end up with a sequence of random variables now which will be of this form. We are now interested in the convergence of this sequence of random variables. Let us start by looking at the LP norm of these. So, here what happens is that xnm, the p norm of that, if you compute again, it is the pth root of the pth absolute moment of the random variable xnm, and this can be computed and this simplified will give you this value. Now, what happens is that as soon as we have chosen our number p between 1 and infinity, we can immediately verify that as n goes to infinity, these LP norms go to 0, and hence what we are saying is that this sequence of random variables in the LP space converges to 0. This is true for any p from 1 and infinity, 1 included, infinity excluded. However, let us now look at the almost sure convergence, whether this sequence converges in the almost sure sense. Now, if we fix any omega between 0 and 1 except 0, then for any such omega positive, what we shall have is that given any number n, we will always have a number small m such that omega falls in such an interval, meaning we will have this inequality being satisfied. So, let us look at this from the pictorial sense. We have the interval 0 1 and we are picking a point small omega somewhere inside. Now, if we subdivide the interval into n equal length subintervals, omega must be falling in one of the subintervals, and that is how we end up choosing the number small m. Now, for that choice of small m, as soon as the omega belongs to that interval, the value of the random variable there must be 1. Now, this choice of small m depends on n, and for each value of n I get one single m such that this condition is satisfied. Therefore, what we are going to do is that if we vary our n, we will get this infinite sequence of points m for which this condition is satisfied, and therefore, the xnm of omega becomes 1. So, therefore, in this sequence of values we will have infinitely many ones. On the other hand, we can again, arguing similarly, we can show that this sequence of values also contain infinitely many zeros. Now, therefore, if a sequence contains infinitely many zeros and infinitely many ones, we will essentially have 0 and 1 in particular being two subsequential limits of the original sequence, and therefore, we will essentially be able to conclude that the original sequence does not converge. So, what we ended up showing is that if you choose omega positive, then the sequence of numbers, they do not converge because they contain infinitely many ones and infinitely many zeros. So, therefore, this shows that on this set of full probability, which is this set 0 1 except the point 0, we do not have the convergence. So, therefore, this sequence of random variable cannot converge in the almost sure sense. So, in the next lecture, what we are going to discuss is another mode of convergence, and we will see various other related comparisons with the convergences that we have stated in these lectures, meaning the almost sure convergence and the LP convergence. So, we stop here. Thank you.